Okay. Um, let me share my screen here.
Recording in progress.
Uh, share. Okay. Can you see my screen?
Yeah, we can see.
Okay. Okay. So I think this. Okay. So today's goal, uh, we'll start with um, phonon bands with dagger operator. It's just basically creation and annihilation operator. Then the tight binding model, just to get the dispersion relation, like how it works, the basics. And then the SSH model, the way to compute the bands is kind of similar. Once you know the Hamiltonian, you can easily compute the bands. And then I'll try to use QE to get the Hamiltonian. And bands. So yeah, so I think I have kind of made notes in the overleaf document for all of these, but it may not be kind of maybe not very compact, like sometimes a little descriptive, sometimes I may have skipped few steps. So if you go through the document, find any kind of missing element, talk to me, or so that we can fill it up. Okay, so first we start with the uh, phonon bands. So if you remember, and tight binding model is they're good for electronic bands. Okay, and this is this model. So for phonon bands, if you remember, we had the Hamiltonian A dagger A plus 1, right? And some were N. And well, for a simple harmonic oscillator, we write down the Hamiltonian like this: 1 over p squared over twice m plus half x, m omega squared x squared. And then we can write it as using a dagger A plus half h bar omega, right? I think we have seen that before in our first or second class. So this is for a single harmonic oscillator. So the idea is here, the important part is a dagger A plus half or plus 1. Half or 1 is just a constant. So the actual feature of those bands or the energy levels will come from a dagger A, not the half. Half is just a shift from shift of the energy band or energy levels from the zero or ground state. So instead of 1, you have many harmonic oscillator, a chain. Then for each of these, so this is the nth harmonic oscillator, you have a dagger and A for that nth oscillator, and the Hamiltonian for that case would be sum of all those A dagger A, right? And we write it like that. H equals an dagger, an plus 1. Plus 1 is just for the shift. And I'm in a unit where h bar and omega is 1 for simplicity, for example. Or we can choose, we can keep h bar omega. But, okay, this is the Hamiltonian without any interaction. No interaction. But to get the bands, we need to include the interactions. And with interaction, the Hamiltonians would be, so the idea is nth atom or site interacts with the next neighbor, so n plus 1. That's the idea. And the way to write that interaction here is, you have a dagger A, say plus a half, or plus, okay, we can do half, we can do 1. It's just a shift. That's the Hamiltonian for free harmonic oscillator, no interaction. Plus, we can add an interaction term. J is the coupling constant or interaction strength. An dagger an plus 1 plus an plus 1 dagger an. So this is the Hermitian conjugate of this first part. Okay, so sometimes we write the Hamiltonian like this: H equals a dagger A plus half, and J a dagger A plus HC. Okay, and you have a sum here, sum over all the n's. Okay, and if we want to include the energy, you can write h bar omega naught, for example, with the first term. Okay, or we can skip it. Okay, h bar omega naught. All right, so what is the Hermitian conjugate? So if you have a dagger B and you take a Hermitian conjugate, then that becomes B dagger A, right? Hermitian conjugate is basically you take an inverse and take a complex conjugate, or transpose. HC is transpose. Rows become columns, columns become rows, and then complex conjugate of all the elements. That's one way of getting Hermitian, Hermitian conjugate of a matrix element. Or you can take an inverse and complex conjugate that. Okay. So that's the Hamiltonian. Now the question is, how do we get the energy bands? To get the energy bands, we need to Fourier transform these elements. Now, about Fourier transform, let me write down, I think someone texted in Zoom, 5 to 7 minutes break. Okay. Now we have the Hamiltonian. Copy and paste. That's the Hamiltonian. And how do we find the bands? So we take a Fourier transformation. An equals ak e to the power, was it a plus or minus? Let me check. it was plus for A. I, K, N, L. K is there, N is there, and okay, that's it. There's a normalization factor in front, but I'm skipping that for now. So sum over all the K's. So a dagger would be, the sum is there, AK dagger, e to the power minus I, K, and L. Okay, because so dagger, when you take the Hermitian conjugate or do a dagger, you take a complex conjugate of all the terms. So if you have z, a complex number, x plus iy, complex conjugate of that number would be x minus iy. Simply I becomes minus I, right? Exactly that's what happened here. I goes to minus I. All right, so that's our transformation. And if you have a n plus 1, that will be ak here, e to the power I k n plus 1 L. Does it make sense? Just n is n plus 1. So we now substitute these here in the Hamiltonian, and let's see what we get. So copy, paste here, and keep this on the side. Okay. Let's see. So first term is a dagger A. What will have h bar omega naught? So if you notice, if we have an dagger, an and an dagger, then on the right hand side we have ak dagger, and we have these two terms. And these terms, if you multiply them together, they cancel out. So e to the power I, K, and L times e to the power minus I, K, and L equal to e to the power I, K, and L minus I, K, and L equals e to the power 0 equals 1. Okay, that means the first term would be AK dagger AK plus a half. Okay, and now we have sum over K instead of N plus J, and here we have an plus 1. So if it's n plus 1, we have ak times, n plus 1 up there. So let me write it. AK dagger, AK, e to the power. So for an dagger, we have e to the power ik and l. So e to the power I, K, and L. For, well, that's dagger, so minus sign. For n plus 1, we have e to the power I, K, n plus 1 L. Okay, and then the Hermitian conjugate. So what do we get? The next line, we have the sum over K, h bar omega naught, a dagger A in K space plus half plus J. Here we get a dagger A in K space, and the exponent, you see, here we have n plus 1, here we have 1. And since if you take a product of two exponential, the exponent gets summed over. So we are left with e to the power I, K, L. Does it make sense?
Yes, sir.
And it's Hermitian conjugate, HC. So next term is h bar omega naught, a dagger A in K space plus a half plus J, the interaction, a dagger A, e to the power I, K, L, plus A dagger A in K space e to the power minus IKL, because that Hermitian conjugate would give you that minus sign. Okay. So that's the expression for Hamiltonian, and you can see that all of these is a function of K. So we can write this in slightly different ways. So the way to write this is we can write it like this. We can take all the A dagger A as a common factor, right? So H bar omega naught plus J e to the power IKL plus e to the power minus IKL. All of these A dagger A plus half H bar omega naught. Sum over K. Okay, because A dagger A is a common common factor, and here okay, we call this H of K, or let's call it small h. A dagger A plus half H bar omega naught. Okay, and H of K here is nothing but H bar omega naught plus J, and e to the power IKL plus e to the power minus IKL. And next line, H bar omega naught plus J, and e to the power IKL and minus IKL. Anyone knows what this formula is? It's really complicated. Is it sine or cosine? Cosine, right? So that's our band for this case. Interaction with just the nearest neighbor. Okay. Any questions? So you can plot, you see this is a single band because we only have one type of atom, monoatomic chain. So the band would be, if you plot H of K as a function of K, you'll have a cosine, and the Brillouin zone will be minus pi over L to pi over L. And you get the cosine there, and there's a shift H bar omega naught. And the half is there here in the Hamiltonian, so overall shift in energy. But the feature of the bands only depends on this cosine KL. Okay. All right. Any questions? Okay. Now we can probably shift to the tight binding model, because for the diatomic chain of harmonic oscillator and the tight binding model are similar. The idea is same. We just apply the Fourier transformation on the operator. Maybe okay. Let me briefly talk about the Fourier transformation. They call it Fourier transformation. So I think I've mentioned this before. Fourier transformation is a way to go from X space to K space and vice versa. So it means that we have the position and we have the momentum. Position or the wave vector. position x with vector k. Or we can go from time to frequency. Okay. So the formula is kind of straightforward. F of k equals f of x and e to the power I k x dx, and there's some normalization factor in front, and f of x would be f of k e to the minus ikx dx dk. Okay. Now, what are these actually? So if you remember if you write just e to the power I theta, that's cosine theta plus I sine theta. And if you plot it in a complex plane, imaginary and real, then e to the power 0, make a table. E to the power I theta, theta. If theta is 0, you get 1. So that's here. If theta is pi over 2, you get I. That's here. And theta is pi, you get minus 1. That's here, right? That means you're basically rotating this way. Okay. So if we change theta, we actually rotate in a counterclockwise direction. So e to the power I n theta, or say I n pi, let's call it pi over 6, and n is integer. Okay, if n is 0, we are here. Excuse me. If n is 0, we are here. If n is 1, we are at pi over 6 degrees. What is pi over 6? 180 over 6 is 90 over 3, 30 degrees, right? Okay, so if n equals 1, we are at 30 degrees here. N equals 2, we are 60 degrees. So we just rotate that way, counterclockwise. Now, what if we have either I, kx? What happens then? Let's say k is fixed, x is variable, and let's say k is pi over 100, 100, or 180. Very small steps. Okay, like 1 degrees at a step, and x is continuous. So what happens then? Then we basically move from this point when x equals 0 in a counterclockwise direction, right? Continuously. Like, k is pi over 180, it's a small number, and x is continuous. That means we move in that direction. So that's what's happening with e to the power ikx. And when we multiply with some factor, f of x, so if we plot f of x, and it's a constant 1. Okay. If f of x is a constant, then that sum, what we're basically doing, we're adding up all these e to the power ikx, right? So if you have a circle and you add up all these vectors, right? Because at each point, this point will have a real and imaginary component, right? And we can imagine that it's a vector pointing in this direction. And in any point on the circle, you can just draw a vector pointing outward. So if we sum up e to the power ikx, then basically we are adding up all these vectors that's pointing outward with the same weight, equal weight. Okay. And when you add up all these, what do you get? So what happens if you add up two vectors that are pointing in opposite directions? Anyone?
They cancel out each other.
They cancel out, we get 0, yes. And if it's in a 2D system, we add up all these vectors pointing outward from the center, we get 0. Or we get the center of the circle, right? When we sum it up. So, okay, so that's our f of k. But if f of x is not, we get 0 except for the center. So that's basically gives you the delta function, right? Delta function is called the Dirac delta function, although I think it wasn't, Paul Dirac made it famous, so it's called Dirac delta function. The property is simple. It's 0 everywhere except where the argument of the function or function distribution is 0. Delta is not a function, but let's not go there. But the idea is we get the delta function. Basically 0 everywhere except when k equals 0. Now, if f of x is not a constant but something else, idea remains the same. F of x is, say, just x. Okay, and we have e to the power ikx. We want to sum it up. Okay, so we take a vector here, and if we want to sum up f of x e to the power ikx dx, then what happens? We take the vector e to the power ikx like that here, right? And we multiply that by a factor x, this x. So it can get scaled up or scaled down. And we keep adding, like for all those points on the circle. And after adding that, we get a result like average of those vector or sum of all those vector, and that is our f of k. Okay, and well, interesting part is that when we integrate out a variable x, the resultant is just a function of the other quantity k, other variable, not x is not there anymore, it's kind of eliminated. And one way to see this is if we do integration of x to the power n, or say just e to the power minus x, x squared y dx from 0 to 5. What's the integration? X cubed over 3 times y, and the limit is 0 to 5. If you plug in the limit, it's 5 cubed over 3 times y. So this is just a function of y, right? We don't have any x after doing the integration. Does it make sense? So f of k is just a function of k. So the idea is we sum this quantity, and sometimes this e to the power ikx is also called the basis or continuous basis. If you remember from linear algebra, we can write any vector as a linear combination of their of the basis vector, right? So these are the coefficient, and x hat, y hat, z hat, they are the basis vectors. We take the sum, we can write any vector in that way. In Fourier transformation, well, we can compactify this using vi, ei hat, and a sum, or if it's the continuous system, by an integration, right? And for Fourier transformation, the idea is similar. We have e to the power ikx, that's the basis, okay? And we have the function as the weight or linear or the coefficient of all those bases, and we do the sum, like a different perspective of looking at this. Yeah, so yeah, basically that's it, because I mean there are other theorems, and you kind of need to look at the Fourier transformations of different functions, like unit function, you got the delta function, and the square function, sine waves, cosine, other kind of lot of different functions, and then probably you'll get the idea like how it works in details. But the idea is same. We just use e to the ikx as the basis, and then just do a sum using f of x as a coefficient. Yeah. So okay, now we are back to the tight binding model. Where is the okay? Tight binding model, or TB. Okay, so for tight binding model, idea is similar, but here we instead of one, for now we have one atom per unit cell, I think, yeah, and later we can include two atoms. So Hamiltonian is A dagger A plus or less than minus, and the tight binding interaction constant, and A dagger A m plus 1 plus the Hermitian conjugate. Sum over n, let's call it a 0. So this is exactly like the previous case, right? So you have one-dimensional chain of atom, and in each unit cell you just have one atom. And if you compute the bands, these bands would be exactly similar to the one we have found before. Now, interesting things happen when we include more than more than one atom, like two atom. Okay. So because we want to see the valence band and conduction band, and to see two bands we need two atoms, like for this model, two atoms per inner cell. Okay, the diagram that I tried to draw in overleaf is kind of something like this. And this is the bond, and then it repeats itself like that, and this is the other bond. So it's like each square is a unit cell, and in each unit cell we have two atoms, right? This is the n minus 1, this is the n plus 1 cell, and we can say they have different or same interaction. So let's call it T2 and this one T1. Okay, T1 and T2, two different kind of interaction strength. So how do we write Hamiltonian for this? For this case, the Hamiltonian would be, so we have circles and squares, right? Let's call circles A and squares B. Okay, so we have site A, site B, and in each unit cell we have two of these, one A, one B. So remember, for on-site term, this is interaction. For on-site term, we just have A dagger A. So here we'll have A dagger A for the on-site term, and the energy for that term is epsilon A, plus we have a second atom B, let's call it Bn, dagger Bn. Energy for that would be epsilon B. So for A, operator is A, and for B, operator is Bn. Okay, and for the interaction, let's assume T1 equals T2 for now, equals T. They have the same interaction strength. And we have An dagger Bn. So what does it do, An dagger Bn? It defines the interaction between this one, A and Bn, or the is it A and Bn? Yes. Then and this one is in the same cell. Does it make sense? Maybe I can write it with green color. And dagger Bn. These two. Okay. And next term would be An plus, let me use red color or different color. Okay. Would be, okay, we have interaction with this one and that one. And we also need interaction with this square and the next cell. So that would be An plus 1 dagger Bn. Does it make sense? Somewhat like how I'm writing the interaction and the Hermitian conjugate of all these. Like, you take two neighboring atoms and write their A dagger and A, or A dagger B. Okay. And then this is the Hamiltonian, if you sum over n. And now we can apply the Fourier transformation. An would be sum over e to the power I k n l a k. Bn would be e to the power I k n l b k. Okay. And if you take a dagger here, we'll have minus sign and dagger. Okay. Just like the previous case. Now, I wanted to try to work out the, plug this in and find the Hamiltonian in terms of A and A dagger. Just plug it in and see what happens. Some term will cancel out. For example, here we have A dagger A. That means this term will cancel out and we'll just have epsilon A, AK dagger, AK. Next term would be epsilon B, BK dagger, BK, right? Minus T. And now I wanted to try to compute these terms. Just write down the expression like on your own. You have like, there are 4 terms. So let's say 3 minutes. Okay, just try 3 minutes. Just think about it. It's in the screen. Try to do it on your own, and I'm gonna show you the solution after 3 minutes. Okay. Okay, so anyone have you found the terms, one or all of them? Yes, no? Yeah, it might be a little something new that maybe you guys haven't done, but you have to talk, right? No, the problem and everything. Okay, so the terms would be this is AN dagger BN. So um, if we write down the dagger part, AN dagger would be to the power I, K, and L minus AK dagger. BN dagger would be e to the power minus I, K, and L, BK dagger. So this for this first term, we just have AK dagger BK. But for the second term, we have n plus 1 in the dagger, meaning we'd have plus AK dagger BK, but because of that n plus 1, would have e to the power minus IKL. It comes from this term, just like the previous example. And the next two terms, because we are taking Hermitian conjugate, we just have BK dagger AK conjugate of this plus BK dagger AK e to the power IKL conjugate of the last term. Okay, and the sum over K. And as it happens, for this case, we can write it kind of in a nice format. So, AK dagger BK, and here we can write EA minus T 1 plus e to the power minus IKL minus T 1 plus e to the power plus IKL EB AK BK. Now let's try to make sense of this. Like how does it make sense? So here we have epsilon A dagger, AK dagger, AK. So if we take this AK dagger, do the multiplication, then epsilon A goes with AK and AK dagger. These three terms gives you that first term. Okay. And if you do the matrix multiplication, you see all these, we can write the, one-line term in terms of matrix, and we get this. And we can try to make sense of the second term, for example. So here I have minus t and minus t to the power IKL. Clearly, it's the non-diagonal term or off-diagonal term. So if we so you take AK dagger, let me erase those for the moment so that it's easier. So you take AK dagger, and if you want to multiply this number, this column, for example, then we have AK dagger and we have AK and okay, we no, that goes with BK. Okay, but yeah, so let me write down the the column for this. So this is for A. This okay, I need row index and column index. For let me use the bracket notation for now. That might complicate things, but okay. AK, this is BK. Okay, that's the column. Okay, so for here I have let me just, okay, I think it's easier if I write it like this: minus T A dagger B plus K e to the power minus IKL AK dagger BK. Now, can we write it in terms of matrix? Just one element. If we take a dagger, was it a dagger B? Yeah, a dagger to the left and B dagger to the right, then you have BK to the right. Yeah, we have this term, right? A dagger BK. And if we want to write like this in terms of matrix, and AK, BK, AK dagger, BK, and 0, 0, 0, just minus T, 1 plus e to the power minus IKL. Now let's do the matrix multiplications. Let's see if we can get this back. AK dagger, BK, and if we do this matrix multiplication, these two matrix, what do we get? We get 0 times AK and minus T times 1 plus e to the power minus IKL times BK. So we get just and for the last row we just get 0. So we get minus T 1 plus e to the power minus IKL BK and 0, right? A column, and this is a row and we have a column there. If we take the product, we get minus T 1 plus e to the power minus IKL AK dagger BK plus 0. Does it make sense, this matrix multiplication?